One of the primary reasons why we're interested in finding a derivative is we're looking for rate of change. And we're looking for an instantaneous rate of change with the derivative, slope of the tangent line. And the instantaneous rate of change tells me what's happening at one particular input value. Okay, so I only have to know one particular input value in order to find the rate of change at that particular point. So we're going to be looking at applying this idea to business problems, which is one of the reasons we really want to focus on this rate of change idea. So here in this example, we're looking at something called the gross domestic product, or the GDP. You've probably heard of that. We're just going to look at a quick little idea of this idea of the rate of change and why we care. The GDP represents the total dollar value of all goods and services produced over a specific time period. Okay, so it says you can think of it here as the size of the economy. Now, a significant change in the GDP, so whether that GDP goes up or where it goes down, is something that people are watching. It has a significant effect on the stock market and kind of is an indicator of what's happening in the economy. Okay, it says here that if we have a negative GDP, so negative growth, then our economy could be going into a recession. So the gross domestic product of a country is something significant, and the rate of change of that gross domestic product would be something that we would be interested in. Okay, so looking at example 16 here, it says a certain country's gross domestic product is given in billions of dollars. Is described by the following function. Okay, so we have g of t equals, and then we have our function, and this is good for t values of 0 to 11. And a couple of things are important. First of all, the output of this function is billions of dollars. Okay, so the gross domestic product, the output here given in billions of dollars. The input, t equals 0, corresponds to the beginning of 2003. So let's just write a couple of values out. T equals 0 corresponds to the year 2003. T equals 1 will correspond then to the beginning of 2004. Talking about the years, basically T represents the years after the beginning of 2003. T equals 2 would be 2005. If I had T equals 5, that would be 2008. So I'm just adding 5 to that beginning year. T equals 7 then would be 2010. T equals 10, of course, would be 2013. So just to give you an idea of what the T values are actually representing. So we go all the way up to T equals 11, which means we go from 2003 to the beginning of 2014. So part A. Part A says, at what rate? Okay, so this is one of the keywords here that we're going to be looking for. Remember, the derivative is the rate of change, the instantaneous rate of change, the slope of the tangent line, how things are changing at that specific point. So at what rate? When you see the word rate, okay, we're looking for the idea of slope of a tangent line, which means I'm looking for a derivative. Okay, so this is one of our keywords, rate of change, important. So we want to know, at what rate was the GDP changing at the beginning of 2008? So the first thing I want to do is actually come up with my rate of change formula, my instantaneous rate of change formula. I want to find that slope of the tangent line formula. So we need to take the derivative of my function g. So we're going to find g prime of t. Well, it's pretty easy. We have 4 terms there. We're just going to use the power rule. 3 times negative 2. I get negative 6t and reduce the power by 1, so t squared. Plus the second term, 2 times 45 is 90. Reduce the power by 1, we get t to the power of 1. 20t, the derivative of that term would just be 20. And the last term is a constant, so we get a derivative of 0, and I'm not going to write it. So part A says, okay, at what rate, or what is the slope at a particular point? So at 2008. So 2008 corresponds to a t value of 5. So we're going to put a 5 into our derivative in place of t, and this will tell us the rate of change, that instantaneous rate of change at the beginning of 2008. Okay, you can just put that into your calculator, basically right as you see it, and we get a positive 320. Now what's important is to remember that this is the slope. Okay, so I'm going to think about it as a slope for a minute. I'm going to think about this as something over 1. So slope is rate of change. So what is it telling me? This is telling me the change in the gross domestic product divided by the change in years. Change in time, change in years. So what we're saying is here the gross domestic product is increasing by $320 billion divided by 1, so that's per year. Okay, so that's what we're saying here. So we know that the gross domestic product is increasing by $320 billion per year at the beginning of 2008. So I'm going to ask us another question. What about the beginning of 2010? So we're going to do the same thing, except 2010 corresponds to a t-value of 7. So we're going to plug in our 7 into our derivative and find out what is the rate of change at the beginning of 2010. All right, throw that into our calculator. I get 356 over 1. So it tells me that the gross domestic product is increasing, so it's a positive slope. It's increasing by $356 billion per year. Okay, and then what about the beginning of 2013? So we're going to plug in a value into our derivative again. 2013 corresponds to t equals 10. So we're going to plug 10 into the derivative in place of t. Oops. Throw that right into my calculator and I get once again 320. So it's telling me that my gross domestic product for this country is increasing, so a positive slope, by $320 billion per year at this particular year. So at the beginning of 2013, we're increasing by $320 billion per year. All right, now part B actually has a little keyword there. It says the average rate of growth of the GDP from the beginning of 2008 to the beginning of 2013. Okay, remember that the average rate of change was going back to the idea of the secant line. Okay, so the key here is average rate. So on average, what's happening over those 5 years? That's what we're looking for. Is the GDP going up over those 5 years? On average, what was the rate of change or the rate of growth? Okay. So in this case, we're going to use the good old-fashioned idea of slope. So for part B, we're looking for an average rate of change. So I'm going to come up with 2 points on the original graph that stand for what's happening at each one of these years. So we're going to do t, and then we're going to see what we get out for g. So for t value at 2008, the t value would be 5. For 2013, the input t value would be 10. I want to know what the y values are, what the output values are for each one of those. So we're going to go back to the original function. Remember, these represent points on the original graph. And I'm going to put in a t value of 5 into the original function, and let's see what we get. So negative 2 times 5 cubed plus 45 times 5 squared plus 20 times 5 plus 6,000. Okay, where am I getting those values? Remember, I'm going back to the original function that I was given. We want to know the actual GDP at those particular 2 years. And for that year, I get, let's see, 6,975 billion. Oops. Okay, then for g of 10, I'm going to do the same thing. We're going to put 10 into the function, the original function, in place of t. Just throw that right into your calculator and I get 8,700 billion. So we're looking for on average how the gross domestic product is changing on average over those 5 years. So we're looking basically for the slope of the secant line that goes through those 2 points. So I'm just going to subtract. I'm going to think about this as kind of like my point 1 and my point 2 here. Oops. It's going to subtract the y values on top, so 8,700 minus 6,975. I'm going to do 10 minus 5, and that gives me 1,725 over 5 years. So keep in mind what we're saying is that there was an increase of basically $1.725 billion over those 5 years. So this represents the billions of dollars over those 5 years. What were we increasing actually per year then on average is what we want to know. So on average, I'm just going to write AVG there. On average then per year, I'm just going to throw that into my calculator and I get $345 billion per year is how much the gross domestic product was changing over the course of those 5 years. And remember, this is an average rate of change. So we were increasing, on average, $345 billion per year. Okay, so part A is asking us for a rate of change at one specific point along the curve, which is the slope of the tangent line. And then part B is asking us for an average rate, and it gives us 2 years, which means we're looking for the slope of the secant line. And that's just the good old-fashioned slope, the average rate of change over those 5 years. All right, for this example, we're looking at obesity in America. And here we're given a function that tells us the percentage of the U.S. population that is obese. All right, so that's what our function is giving us. I'm just going to kind of highlight this idea right here about what the function is giving us. So the output tells us the percentage. The input is measured in years, t equals 0, corresponding to the beginning of 1991. Part A asks, what is the percentage of the U.S. population that was deemed obese at the beginning of 1991? So what's really important is Part A and Part B, they're distinguished, separate from each other, in that Part B, the first thing it says is how fast. So Part A is not asking us for a rate of change, it's just asking us to use the original function to find the percentages, not a rate of change. So we're not finding a derivative here, we're just going to plug into the original function. So at the beginning of 1991, that's represented by a t-value of 0. We're going to plug that back into the original function. If t equals 0, I think we can pretty obviously see what's going to happen to the first 3 terms. They're going to become 0, and then we're going to say plus 12. So what we get is, in the beginning of 1991, there was 12% of the U.S. population that was obese. All right, what about, next question here says, what about the beginning of 2010? What was the percentage of the U.S. population that was obese then? So 2010 corresponds to a t-value of what? So remember, we're talking about years after 1991. So how many years after 1991 is 2010? So you could do 2010, then you could subtract off 1991. And we get the years after that would be 19. So this corresponds to t equals 19. All right, so this one's a little bit more interesting. When I plug 19 into the function, we're actually going to get something a little bit more interesting out. Can't just do that into our heads. And I'll throw all this into my calculator, basically exactly as we see it, and I get 31.2432. I'm going to go ahead and round to the nearest tenth. So I get 31.2%. So 31.2% of the population was obese at the beginning of 2010. So it looks like the trend of obesity is to rise. It looks like the rate of change, the percentage is increasing. So let's look at part B. How fast was the percentage of the U.S. population that is deemed obese changing at the beginning of 1991? So how quickly was this obesity percentage rising at the beginning of 1991? So basically we're looking at per year how many people were becoming obese. How was that percentage changing? So in this case, since we're talking about how fast, we're talking about a rate of change, then we need to find a derivative. So that's the first thing that I'm going to do. I'm going to find the derivative of our function. So we're going to use the power rule. Now we have some decimals, but that's okay. You have a calculator that you can use. So 0.0004 times 3. I'm going to multiply those values together. Reduce the power by 1, so it's t squared, plus 2 times 0.0036, and once again, you can use your calculator here. I get 0.0072, and then we reduce the power by 1, and just get t to the power of 1. And then the last term, I have a constant times t, so that just gives me the constant value, 0.8. And then the last one is a constant, and the derivative of a constant is 0. So I'm going to end my derivative right there. So the first thing I need to do is find the derivative. And then I want to know how the percentage is changing at the beginning of 1991. So for 1991, I'm going to plug into my derivative the t value of 0. Okay, and once again, pretty easy. We get 0, 0 plus 0.8. So it's increasing. What's my rate of change? It's increasing at a rate of 0.8% per year. Because it's a positive value, that's how I know it's increasing. It's going up by 0.08% per year. So it's not going up too fast. But what about at the beginning of 2010? How many people are being added to this percentage of obesity here? So in this case, I'm going to plug in a value of 19. And once again, gives me something a little bit more interesting. I'm going to throw that right into my calculator, and I get 1.37. I'm going to go ahead and round that to the nearest tenth, so I get 1.4% per year. Okay, think about that as a slope. I think about that as over 1, so it tells me per year. All right, so the percentage is increasing by a greater amount per year as the years go by. So we're adding 1.4% of the population per year in 2010, whereas in 1991 we were only increasing by 0.08% per year. Right here in this example, we're looking at middle class income, and we're given a function that tells us the percentage of households that have annual incomes within 50% of the median income. In other words, what percentage of households are what we would call middle class. Here our output is given in percentages. The input is t measured in decades, with t equals 1 corresponding to 1980. So let's just write out kind of what our input values are representing. T equals 1 corresponds to 1980. So then t equals 2 would correspond to the next decade, 1990. T equals 3 corresponds to the next decade, so 2000. And then t equals 4 corresponds to 2010, and so on. Okay, all the way up to t equals 6. The first question we're asked is what percentage of households had annual incomes within 50% of the median income in 2010? In other words, what percentage of homes were middle class in 2010? So we're going to use t equals 4 into our function. Notice that it's just asking us for a percentage. It's not asking us for how the percentage is changing. It's just straight, what is the percentage? So I'm going to use, for part A, we're just going to use the original function. And for our t value, we said we're going to put in a t value of 4. So here we're actually taking our value and raising it to a negative exponent. All right. All right, we put a 4 in. You basically can put this right into your calculator as you see it. If you're using a scientific calculator, then you would do something like this, 50.3 times, and I would do 4, lose my little caret symbol, and then put in parentheses the little negative sign, and then my 0.09, and then see what we get out. So when I put this into my calculator, I get 44.399, and I'm going to go ahead and just round to the nearest tenth, so I get about 44.4%. So in 2010, about 44.4% of households were middle class, considered middle class. All right. Part B, we're asking for how fast that percentage was changing. So what is the rate of change? And it says it's decreasing. The middle class, the percentage of homes that are middle class, it says here that it's been in the decline since the 1970s. So less and less people are considered to be middle class. But how fast is it changing is what we want to know. So if I want to know how fast something is changing, of course, we're going to find a derivative. That's rate of change. So I'm going to first of all, take the original function, and we're going to take the derivative of that. And we're using the power rule. Okay, so we have t raised to this exponent. So we're going to take that exponent and multiply it. So I have 50.3 times negative let's put the 0 there, negative 0.09. And then I have t, and I'm going to reduce that by 1. So if I subtract 1 from that, what do I get? Well, let's simplify that. Okay, so I get, in my calculator, that tells me I get negative 4.527 t, and then when I put this into my calculator, it gives me negative 1.09 as my new exponent. Okay, remember it gets more negative when we take a negative exponent and subtract. So we are looking for something specific. Remember, this is the formula that tells me the slope, the rate of change at any particular x value. What is the value that we're putting in as input? Well, we want to know about the year 2010, that decade, which corresponds to a t value of 4. So we're going to put that t value of 4 into our derivative and see what is that actual rate of change for 2010. Once again, you're going to do something similar up here. I'm going to use that little caret symbol and put in my parentheses and then put that negative exponent in the parentheses. Okay, then I get something like this, negative 0.998999, and I'm going to go ahead and round that once again, kind of round that to the nearest tenth. And when I do that, it actually rounds the whole value up to about 1%. So it looks like the percentage of middle-class income families is decreasing by 1% per decade. Okay, so you can think about this if you want as negative 1% over 1. Think about that as a slope. And then remember that this was representing the number of decades, or decades after 1980. Okay, so it's decreasing by negative 1% or decreasing by 1% per decade. Okay, in our last example for this section, we're looking at a demand function for walkie-talkies. Remember that demand functions correspond quantity demanded and the unit price. So it kind of shows the relationship between those two variables. So we're given our function here where x represents quantity demanded in thousands, and that's important, and p represents the unit price in dollars. So the first thing that we're asked to find is the derivative. What is the rate of change? In other words, how is price changing corresponding to quantity? So we're going to find the derivative. We're going to use the power rule for each term individually. So the first term, using the power rule, I get 2 times negative 0.1. So it gives me negative 0.2, and then reduce the power by 1, so I just get x to the power of 1. The next one is a pretty easy one. I just get the constant that's multiplied in front of x. And then the last one is a constant term, which means we get a derivative of 0. Okay, remember this is measuring, I'm just going to write this down, this is measuring the change in price over the change in quantity. Okay, so this is what we're talking about when we're talking about the derivative here. Change in price, how the price is changing with respect to how quantity is changing. So it says, what is the rate of change of the unit price when the quantity demanded is 10,000 units? So something we want to be careful about is we're talking about x representing quantity already in thousands. So when you actually use this number, x or the quantity demanded is 10,000 units, you want to say x is equal to how many thousand. So you need to be able to write the word thousand after the x value that you plug in. So we're going to say x is represented by 10,000. So I'm not going to plug 10,000 into my derivative in place of x. I'm going to plug in 10 that represents that many thousands. So we're going to plug in 10 into our derivative. Okay, when I do that, I get negative 2.4. I'm going to go ahead and put a 0 there to represent kind of the price there. I'm going to think about this as a fraction because we're thinking about it in terms of slope. So what this is telling me how the price is changing corresponding to the quantity. Okay, what does this mean? So I'm going to go ahead and write this down kind of in words. So notice that the price is negative. So that tells me that it's going down. Okay, so the unit price is going down. And the bottom number is positive, so that's divided by a positive 1. So this tells me that the change in quantity is increasing. If you sell 10,000 units, the price is going down by $2.40. Let's think of it the other way. So if you reduce the unit price by $2.40, what that tells me is that the change in quantity will actually increase. So you will actually sell 1,000 more units if you decrease your price by $2.40. What is the unit price at that demand? So how much am I actually charging if I'm actually selling 10,000 units? In this case, I need to go back to my original function. I need to go back to the function that actually tells me the unit price, not the change in unit price, but the actual unit price. So I'm going to go back up to that original function, and we're going to find the price when 10,000 units are sold. So I'm going to go back up to the original, plug in a 10, representing 10,000 units being sold, and what is that unit price? And throw all that into your calculator, and I get that the unit price is $21. So $21 per unit, that's my unit price when 10,000 units are demanded.